Welcome to Parallelograms. So we're going to learn the features of a parallelogram, and we're actually going to prove every one of the special features of a parallelogram. Actually, every one except for one. I didn't prove one of them. So objectives for this lesson are to recognize the conditions that ensure a quadrilateral is a parallelogram. And that's the one we'll be focusing on in this particular lesson. Later on, we'll also be solving for measures in parallelograms. Now, quadrilateral, that just means that the figure has four sides. So it's just a four-sided polygon. All right, so this is the first piece of information about parallelograms. I would like to make sure you have this in your notes. Right there, and it is just the sum of the angles, and this is the sum of the angles in any polygon, is found by multiplying 180 by n minus 2. And n is just the number of sides. Now, this is an important formula. The 180 degrees part is the degrees in the angles of a triangle. N is the number of sides in the polygon, and n minus 2 is the number of triangles. So in other words, as you can see here, a parallelogram can be divided into two triangles. Right? So that means that the sum of the angles in a parallelogram would be 180 times, so it has four sides, so n equals 4. So it would be 4 minus 2. 4 minus 2 is 2. So 180 minus 2 is 360 degrees. So all the angles in a parallelogram, or actually any quadrilateral, add up to 360 degrees. And that's actually what I have right over here. So a quadrilateral is a two-dimensional figure that has four sides and four angles. The sum of the angles is 360 degrees. And now you see how we got that. A parallelogram is a type of quadrilateral. It's a type of quadrilateral with both pairs of opposite sides parallel. Now that is not the only way to prove a figure is a parallelogram, as you'll see in these lessons, but it is the definition of a parallelogram. So DC is parallel to AB and DA is parallel to CB. We know that because of the parallel markings. You see this side here and this side here, they have two arrows, right? So that means that those two sides are parallel to one another. These two sides, AD or DA and CB, have one arrow on them. That means those two sides are parallel. So those arrows are the markings for parallel sides. Right, so this figure here, ABCD, is a parallelogram. And because it's a parallelogram, we can put this little symbol here. This symbol is only used when a figure is a parallelogram. Right, so that's the symbol for parallelogram ABCD. So conditions for a parallelogram. In your notes, you have, I believe it's at the top of the page. I don't have a set of notes right in front of me, but I know you have a parallelogram like this in your notes. Right? And we're going to put all the features on this. We're going to keep coming back to this figure and add the features. This is a great way to sum up all of the features of a parallelogram. Right? So the definition of a parallelogram is if the opposite sides of a quadrilateral are parallel, then the figure is a parallelogram. Right? So, but are there other ways to determine if a figure is a parallelogram? And that's what we're going to learn in this lesson. But the first thing we're going to do is we're going to put the markings for the parallelogram, the markings that we know for a parallelogram. So let's call this figure A, B, C, D. And we have just learned that a parallelogram is a quadrilateral with two pairs of opposite sides parallel. So let's go ahead and put the markings on the parallelogram, and we'll also write the information down. Right? So on the side here, let's write AB is parallel to CD, and we should make those segments because they do stop. And AD is parallel to CB. All right, so just put that in your notes for now. And then we're going to prove the rest of the features of a parallelogram in some upcoming proofs. So normally, if this were a live class, I would have you tell me the reason why, but because I'm all alone here, all alone, poor Miss Michelle, she's going to have to, I'm going to have to answer my own questions and give the reasons. All right, but I have my handy dandy arrow here. We just can call him Pointy. And he's going to point to where I'm talking about so I can point out the clues so that you will be able to figure out why the reason is the reason that it is, for lack of a better way to say it. So why is that the reason, right? So for each one of these. So my first statement that I made is AB is congruent to CD and AD is congruent to CB. Well, how can I make such a statement? Well, it's where we usually start. It's with the givens. All right, so it's given. We're told. I don't have to guess. I don't have to wonder. Actually, we'll never guess in these. I don't even have to figure anything out. We're given that. All right, so that is a given. That's always a good place to start. All right, so now I want to actually prove that a figure is a parallelogram because the opposite sides are parallel. Now I know whether it's true or not that whether or not a figure must be a parallelogram if opposite sides are congruent. But you don't know that yet. Right? So one way I could go about proving that this could be a parallelogram is if I could get maybe the triangles congruent, and then I could prove angles congruent. And then if I knew angles congruent, well then I could get sides parallel, and then we know it's parallelogram. So that's my plan here. I've already divided this into two triangles, and I'm free to connect points A and C. And because I've actually connected them, I'm going to make the next statement. I'm going to say that AC is congruent to AC. Now, how would I know that AC is congruent to AC? What reason could I have to make such a statement? Well, the reason I have is the reflexive property. Any side, any angle is congruent to itself. You're congruent to yourself, so that's why I can make such a statement. Now that I've made such a statement, I can now also say that triangle ABC is congruent to triangle CDA. Now remember, there's 4 ways we can prove triangles congruent, and I hope you can see in the diagram up above that which of those 5 reasons must apply. Notice that all the corresponding sides are marked congruent. Well, that reason must be side, 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 triangle congruence postulate. Of course, that's why the triangles are congruent. And if I know the triangles are congruent, well, I know these corresponding parts are congruent. Because congruent means all the corresponding parts are congruent, not just the sides, right? So that means that angle BAC would have to be congruent to this angle that it corresponds with, right? So the angle BAC, and all you have to do is look at the ordering of the points in the triangles. So BAC corresponds with DCA. Right, so DCA, let's mark that. And I'm going to erase this part again. And DA, I guess I decided to switch the ordering here. BCA, which is BCA, has to correspond with DAC. So let's mark BCA. So BCA, which is right here, corresponds with DAC. Right? And we know that to be true. Remember that important theorem that says important postulate that says if the triangles are congruent, all the corresponding parts are congruent, and its corresponding parts of congruent triangles are congruent. Very important, right? Because it allows me to take a shortcut and prove other things are congruent. Well, now I mark some angles congruent there. And those angles are on opposite sides of that transversal, and they're between the lines AB and DC, right? And they're also between the lines AB and CD, right? So I know if those angles are congruent, that the sides that created those angles have to be parallel. This is the converse of alternate interior angles postulate, right? Sides are parallel because the alternate interior angles are congruent. So anytime you have 2 lines and they are divided by a 3rd line, if those angles between the lines on opposite sides of the transversal, in other words, the alternate interior angles, if they're congruent, the sides have to be parallel. There's no two ways about it. Well, now if I know the opposite sides are parallel, we just learned on the last page that a parallelogram has two pairs of opposite sides parallel. Right? So now we were able to, using just the fact that the opposite sides were congruent, we were able to prove it's a parallelogram. And this is the exact same way that it was done a long, long time ago. The Greeks determined that, knowing that two pairs of opposite sides congruent was enough to prove a figure to be a parallelogram, because they could do a proof just like we did, right? And then you can see, well, it was enough just to know the opposite sides were congruent. Right? We could prove the opposite sides were also parallel, so this must be a parallelogram. And now you've got another way to prove a figure is a parallelogram. If both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So if we know that AB is congruent to TR, and BR is congruent to AT, what else do we know? We know that BRTA, it's not a brat, BRTA is a parallelogram. No two ways about it, because it has two pairs of opposite sides congruent. All right, so now let's mark that in the figure. So now you're going to go back to the same figure. You already have AB is parallel to CD and AD is parallel to BC. You already have this, right? So we're going to add the other piece of information that we just learned. We learned that if AB is if this is a parallelogram, then AB is also congruent to CD. And AD is congruent to BC. And I may have written them on a different order on the last page, but it doesn't matter. It's the same segments. Right? But now you add in that they're also congruent. And let's also mark that in the diagram. All right? So these two sides are congruent, and these two sides are congruent. All right? So now we're summing up all the information about a parallelogram. But gee, is that the only way? The only two ways we could prove a figure is a parallelogram? Maybe there's more. All right, so now we're going to start off with some information. All right, there's my figure, and it's labeled. And I think there's a typo because I have this step handwritten. So you might want to check out your notes and see if that's miswritten and just fix it. All right, so, and by the way, these are all in your notes. All right, if I go too fast, you just pause the tape and write them in. They're going to come in handy, trust me, later on. All right, so make sure you take notes. All right, so the first thing I'm going to say is BC is parallel to DA. Well, how can I make such a statement? How could I say such a thing? Well, hopefully you happen to notice it right here under the givens. I can make such a statement because that is given. We know that piece of information. Oops, this is going by too fast. I want to talk about step before I go writing things down. So I'm going to mark in the diagram that BC is parallel to AD. Now I've got the statement that DAC, right, that's this one here, DAC is parallel to BCA. There we go. Well, how can I say such a thing? Well, this is very similar to what we had in the last proof. Right? We've got parallel lines cut by transversal. So if we have parallel lines cut by transversal, the alternate interior angles that are formed by those parallel lines are congruent. Right? So alternate interior angles formed by parallel lines are congruent. Now I'm going to make another statement. I'm going to say that AC is congruent to AC. Well, we had that one on the last slide, so hopefully you remember that any segment is congruent to itself. That's the reflexive property. Right? And now I'm going to say BC is congruent to DA. Now, why can I say that? Why can I say BC is congruent to, I have to use two because I already used one, is congruent to DA? Well, hopefully you always look back up here. Now, lots of times I use both of the givens together at one time. But here I used one given and the other given. So I needed to use the first given, that BC parallel to DA, because I wanted to get the alternate interior angles congruent. And you might be thinking here, well, I've got that figure divided into two triangles. I'm proving stuff congruent. Maybe I'm going to prove triangles congruent. And then I can get all kinds of things congruent. Well, you'd be right if you said that. So I started off with the parallel lines so I could get a pair of angles congruent. And then I went to the reflexive property and the other given. And actually, so BC is congruent to DA. That's a given. And now I can say the two triangles are congruent. So you're going to see a pattern here. It helped me out if I would just be able to prove I have two congruent triangles. So then I can get other stuff congruent that we already know proves a parallelogram congruent. All right? So that's my method here. And now think to yourself, which of the triangle congruence postulates would prove the triangle's congruent? All right? So now look, you've got, I don't have all three sides, so it can't be side, side, side. I only have one pair of angles, so it can't be angle, angle, side, or angle, side, angle. It's not a right triangle. But I've got two sides and the included angle congruent. So this is side, angle, side, triangle congruence postulate. Now that I know the triangles are congruent, we now know that AB, and I'll have to use three lines to mark these, is congruent to CD. And how do we know this? Well, we prove the triangle is congruent. And we know if the triangle is congruent, all the corresponding parts are congruent. So corresponding parts of congruent triangles are congruent. That's how we know that that other pair of sides is congruent. And well, now we know that this has to be a parallelogram, because on the last page we said that if we had a quadrilateral and both pairs of opposite sides were congruent, that it was a parallelogram. And now look what we got. We have a quadrilateral with both pairs of opposite sides congruent. So ABCD is a parallelogram, our last reason here, because both pairs of opposite sides of a quadrilateral are congruent. And that's only true if the figure is a parallelogram. All right, so now we've got some more things to write down on our figure. If one pair of opposite sides of a quadrilateral is both parallel and congruent, then the quadrilateral is a parallelogram. All right, so back here when we were proving it, let's go back and look. So I used the one we had already learned, that two pairs of opposite sides of a quadrilateral, if they're congruent, the figure is a parallelogram. But what we were given was not that. We started off with one pair of opposite sides parallel, one pair of opposite sides congruent. Right, so if you go through our proofs here, the only one I gave you, which was the definition, is that if two pairs of opposite sides of a quadrilateral are parallel, the figure's a parallelogram. All right, so that we were given. And then we started off with a proof that was both pairs of opposite sides congruent. And we were able back here to prove that the figure had to be a parallelogram. So if we had two pairs of opposite sides congruent, we could show that we also had two pairs of opposite sides parallel, and the figure was a parallelogram. Over here, we were given that one pair of opposite sides, keep on going, one pair of opposite sides was congruent, and the same pair of opposite sides is parallel. So we had one pair of opposite sides that was both congruent and parallel. And then we were able to show that we really have two pairs of opposite sides congruent, right, by proving triangles congruent. And so now we have another way to prove triangles congruent. So now we have three ways. If we know we have if a quadrilateral has both pairs of opposite sides parallel, it's a parallelogram. If a quadrilateral has both pairs of opposite sides congruent, it's a parallelogram. And if a quadrilateral has one pair of opposite sides parallel and congruent, it's a parallelogram. So look at that. We've got three ways now. All right, so if one pair of opposite sides of a quadrilateral is both parallel, I can say that, is both parallel and congruent, then the quadrilateral is a parallelogram. And it doesn't matter which pair of sides, so long as it's one pair of sides. It can't be one pair of sides parallel and a different pair congruent. No, that won't work. Has to be one pair of sides having both characteristics. Now, this is the only one we didn't set out to prove. if both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So this one I didn't prove. So here angle A and is congruent to angle P. Angle W is congruent to angle Q. And so if you have a quadrilateral and it has both pairs of opposite angles congruent, then it must be a parallelogram. Let's mark that in the figure here. All right, so, and notice that I have a different figure each time, so the colors keep changing, but that doesn't really matter. Angle A is congruent to angle C, and angle B is congruent to angle D. So mark that in your diagram and write that down. All right, so now you have you have 4 ways to prove a figure is a parallelogram. You can't really write down the pair of sides parallel and congruent because we've already got both pairs of sides marked congruent and parallel. So we didn't put that one in our diagram. And this one I didn't prove either. So if an angle of a quadrilateral is supplementary to both its consecutive angles. In other words, if you know one angle, and if we took either of the consecutive angles, so if this is x right here, this one's a consecutive angle, and this one is a consecutive angle. It's the ones next to. Right? So together, those 2 angles, if they add up to 180, so you have both pairs of consecutive interior angles supplementary, then this has to be a parallelogram because consecutive interior angles are supplementary only when lines are parallel. All right? So the fact that you have consecutive angles supplementary means that the lines are parallel. So let me erase this here so I can kind of show it. Oop. All right, so if these 2 are supplementary, then these sides are parallel. So it would be this side here and this side, right? The sides that the angles are between. And then if these 2 angles are supplementary, then these 2 sides are congruent. Oh, where am I going to fit it in? How about over here? Then these 2 sides are parallel. Right? And then I can put the little parallel markings there. Right? So when consecutive angles are supplementary, the sides they're between are parallel. And that's what gives us 2 sets of parallel lines, and that means this is a parallelogram. So if a quadrilateral is a parallelogram, then its consecutive angles are supplementary. In other words, angle M plus angle Q equals 180. Here, I'll just move this here. Hey, where's an M? Angle, so did I say M? The measure of angle P plus the measure of angle Q is 180. So P plus Q equals 180. So here's P and Q. They add up to 180, and angle Q plus angle R add up to 180, and angle R plus angle S adds up to 180, and angle S plus angle P adds up to 180. Right? And then as a little reminder, consecutive angles of a polygon are angles that share a side. They're next to one another. So these 2 are consecutive, and this one are consecutive, and this one are consecutive, and this one are consecutive. All right, so consecutive angles are supplementary because they are same side interior angles formed by parallel lines. So since QR is parallel to SP, then angle Q plus angle angle Q plus angle P add up to 180, and angle R plus angle S add up to 180. Those are the consecutive interior angles for those ones. And then since PQ is parallel to SR, then angle P plus angle S add up to 180, and angle Q plus angle R add up to 180. Right? So we have 4 pairs, right, of consecutive interior angles, right? So these two, P and S and Q and R, are the consecutive interior angles for QP and RS, right? And then P and Q, did I say that one? I don't think I did Q and R. So Q and R and P and S are the consecutive interior angles for lines PQ and RS. And then, who did I miss? I missed somebody. Oh, Q and, no, I did that one. Oh, I don't know who I missed. Well, anyway, I have them up there. Q and P, R and S, that goes for QR and SP, and Q and R and P and S, that goes for lines PQ and SR. I kept forgetting which ones I said. So that's why I pays to write it down. Now I've almost proved all the things that we need to prove and made all the markings we need to make. Let's make the markings on this one. We're going to prove one more thing, and then we'll make markings again, and then we're going to stop this video. All right, so these are the things we've already written down. Now we're going to write down the consecutive angles that are supplementary. And when I write them down, I won't forget what I said. So angle A plus angle B adds up to 180. Angle B plus angle C adds up to 180. Angle C plus angle D adds up to 180. And angle D plus angle A adds up to 180. Right? And they are all consecutive interior angles formed by parallel lines. All right? So there we've written down the information from the previous proof. Let's do one more proof. All right, so this one you'll have to put, I forgot to put this one in your notes, so I'll have to do this one on paper. I have all the steps written out, and then we'll go over the reasons, right, as we go through each one. Oh, and I don't have, where's Pointy? So I can point. There he is. Okay. All right, so I'm going to start off with, so first of all, I wanted to point something out to you. So AC, right, so AC, whoops, come on, Pointy. AC and BD are diagonals of figure ABCD. A diagonal just goes from one point to a non-adjacent point, right? So it can't go from D to A because those are adjacent. It can't go from D to C because those are adjacent. But it can go from D to B because those are not adjacent, and A and C are not adjacent. All right, so the first thing I decided to say is AM is congruent to CM and DM is congruent to BM. And I hope you have no trouble figuring out why I said that. Why could I have said that? I can't imagine why I said that. All right, so that was given. All right, so definitely starting off with the given here. Whoops, and I guess it got erased. That's okay, whoops. Well, we're giving away angle reason 2 here while we're fixing reason 1. Well, there we go. All right, so now I decided to say that, so I've got all those little sides there that are congruent to one another. I've no sides on the, I've got all those sides of the triangles that are congruent, but I have no sides on the quadrilateral, right? So, and I have no way to get any based on the information I have. However, I could say that angle AMD is congruent to angle CMB. Right? Now, why can I make such a statement? What kind of angles are these? Why, they are vertical angles. Okay, this is the vertical angle theorem, which you probably saw. Whoops. Well, you probably didn't have any trouble figuring out why the triangle is congruent. And you probably saw that when I moved the slide earlier, but those are vertical angles. They are angles formed by intersecting lines. They are opposite one another, and they are always congruent. Because those two, we have two sides, we have the angle between. That means triangle AMD is congruent to triangle CBM using side angle side triangle congruence theorem, right? So that's this triangle here and this triangle here, right? But I'm going to move that out of the way because it'll get too busy after a while. So let's just get rid of that. All right, so I'm done with that little piece of information. All right, and now that I've said the triangles are congruent, so like I said, I have no sides on the quadrilateral that are known congruent. I can now say that AD, I'll have to use 3 lines, AD is congruent to CB, and I can say that because we proved the triangle is congruent. So corresponding parts of congruent triangles are congruent. If the triangles are congruent, all the corresponding parts are congruent. All right, so, well, it doesn't want to, it wants to do its own thing, apparently. Well, besides just knowing that the angles that I marked are congruent, we also know that angle AMB has to be congruent to CMD because they are also vertical angles. Angles that are opposite one another formed by parallel lines. By intersecting lines. Right? And I bet you have no trouble figuring out that the triangles are congruent using side angle side triangle congruence theorem, right? Just like before. I have no hope. The slide's just going to move at its own pace. Right? We've got 2 pairs of sides and the angles between them. That would be side angle side. And of course, if the triangle is congruent, all the corresponding parts of the triangle are congruent. So that means AB has to be congruent. Now I got to use 4. AB has to be congruent to CD. And now we know this has to be a parallelogram because we have both pairs of opposite sides of a quadrilateral congruent. Right? And we saw way back that if we had 2 pairs of sides of a quadrilateral congruent, that would have to be a parallelogram. Now, I could have used other ways to prove this was a parallelogram, but this was the easiest, right? Just getting the triangles congruent, and then we could get both pairs of opposite sides congruent. All right, so now, and if you needed to pause this to write things down, go right ahead. I'm going to just go through the conclusion here. All right, so this is our last way we're going to learn to prove a quadrilateral is a parallelogram. If the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram, because that's the information we started with, right? We started with diagonals where they were broken into 2 congruent parts, right? So MD is congruent to BM, AM is congruent to CM, and if something is bisected, it means that it's divided into 2 congruent parts. So if a segment is divided into 2 congruent parts, it's bisected. And if we have both pairs not both pairs, there's just 2, both diagonals bisected, then the figure has to be a quadrilateral. So here, since HG is congruent to MG, then diagonal HM is bisected. Since BG is congruent to PG, diagonal BP is bisected, and this has to be a quadrilateral. So this particular figure, HPMB, is a quadrilateral. And I think I'm going to end here. And in the next video, I'm going to go, actually, I'm not going to end here. I'm going to end on this one. Let's add in the pieces of information, all right, so that we have all of our features. All right, so I forgot to erase, on each one of these, I've erased it from a previous lesson. I did not erase the diagonals, so mark that DM is congruent to BM, AM is congruent to CM, and then let's write that in our notes. So AM is congruent to CM, and DM is congruent to BM, and next to that put both diagonals are bisected. So now your parallelogram should look like this, summarizing all the information we learned. And that's going to be the end of this video. In the next video, we'll sum up all the ways that we have to prove a quadrilateral is a parallelogram, and then we'll go about proving quadrilaterals or parallelograms. All right, thanks for watching. Bye for now.